Hello, my name is Keywoong from Inha University in Korea. Today I'm gonna introduce about my paper Bimodal classification with CNN and sequence models. CNN-based classification models have made a remarkable advance, and MNIST public data sets can yield over 99% accuracy. The sequence MNIST dataset, which represents the stroke order of MNIST public data as a vector, can also produce more than 95% accuracy if trained with an RNN-based model, for example transformer model. However, these public datasets are generated in a standard environment and do not include frequently occurring variations in the real world. In other words, when errors are included, the performance is rapidly degraded. A single model is bound to be vulnerable to errors because it receives only one type of dataset. Even though the transformer model has usually represented a good performance among sequence models, but the accuracy decreases significantly when the corrections are included on the datasets. So in this study, we're gonna solve these problems by using bimodal classification model. The multimodality is a structure in which two or more different modals are integrated for the deep learning architectures. Learning using multimodal receives several sources and connects the information in the various layers in the architectures. Multimodality has several advantages. First, the multimodal model allows for flexible use of input nodes, including alternating and combined use. This improves error tolerance and accommodates a wider range of user, operational, and environmental situations. They can adapt to constantly changing environmental conditions and accept individual differences, such as permanent or temporary handicaps. Due to these characteristics, multimodal recently achieved excellent performance in model generalizations that can learn by receiving different features simultaneously. In this study, we propose a bimodal classification model using two unified models with the CNN and a sequence transformer model can achieve the better result than unimodal for the erroneous and curved datasets. The MNIST dataset consists of about 60,000 training datasets and 10,000 test datasets. The shape of the image MNIST dataset is 28,28,1. The sequence dataset is a sequence vector dataset represented in the order of skeletal strokes of the image MNIST. A common method for image thinning is applied. After the thresholding and thinning steps, the result is a skeleton of the original digit image that must consist of single pixel with white lines. This is a four-dimensional dataset. In the first and second dimensions, the degree of change in the x and y values is expressed as vectors. The third dimension is EOS, end of stroke, which marks the moment the pen takes off the paper as value 1. The fourth dimension is EOD, end of digits, and the last moment is denoted as value 1. Thus, at the end of a total of 70 sequence datasets, EOS and EOD both are value 1. Next is the Gaussian coefficients. Gaussian coefficients has the same probability density function as the normal distribution, and it is a general noise without any bouncing noise. It is characterized by a distribution that occurs randomly to some extent and is generally easily applicable to achieve. The probability density function for the Gaussian coefficient is as follows. Z represents the grade level, mu the mean grade level, and sigma is its standard deviation. In the first experiment, we used Gaussian coefficients. The Gaussian corruption is added to the image MNIST dataset and the sequence MNIST dataset, which allows the normal distribution 0,0.9 squared. The experiments were conducted a total of 5 times, and the result values were expressed in the table 1 by calculating the average of the actual accuracy values. As a result, CNN model and transformer model showed accuracies 86.93% and 75.85% respectively, and the result of bimodal model learning was 89.55%. Spike corruption is the generation of points that deviate significantly from the range of noise values in the general form. The spike corruption generation method is to randomly select an arbitrary index and insert an arbitrary extreme value. The second experiment is the experiment using spike corruption. The image MNIST dataset contains arbitrary pixels. Values are between 0 and 255 in any index of 90% of the total number of pixels, 784. In the sequence MNIST dataset, 90% of the total number of sequence vectors was randomly selected and replaced by the arbitrary values between -5 and 5. Average values were obtained by learning a total of 5 times, and the results were shown in Table 2. As a result, CNN model and transformer model were 94.18% and 74.66% respectively, and the result of bimodal model learning was 95.15%. This paper proposed the bimodal models using homogeneous features can achieve good performance even if the data has been corrupt. The experiments were conducted by dividing the dataset into the cases where Gaussian corruptions and spike corruption were included. The result of the experiment represented that the bimodality performed much better than unimodal model in the experiment with the addition of Gaussian and the spike corruptions. In conclusion, it can be seen that bimodal has a robust capability and thus predominates in the generalization of the model, so that multimodality will be much more promising even for the ununified data. Thank you for listening to my presentation.